Yet another day. The things are really interesting. Um, the first image of a black hole was constructed recently by the international team of the Event Horizon Telescope. The image area surrounds the supermassive black hole in the center of the galaxy. MIT-7, the observations resulting in the final image were carried out at a wavelength 1.3 times 10 to the power minus 3 meter, where the interstellar extinction is not prohibitively large. So we don't care about the tau. How large an instrument would be needed to resolve the shadow in effect of the photon capture radius, which is three times the size of event horizon of a supermassive black hole in the center of a galaxy? Express the result as a function as a distance c and mass m black hole. If I do question number one, guys, question number B, question number C, those all these things like it is just about putting in the values. So let us do question number one. How large an instrument is needed, right? So let us suppose that radius of event horizon, radius of event horizon be, let's say, r. Then we have this big thing, big r as 3r, because we have seen that, like, yes, it's three times the size of the event horizon, the Ferdinand capture radius, the event horizon. What we do have here is, let's suppose this is this and this right here with alpha. Suppose this day is going to be 2 or all. So we know for a diffraction limited instrument, I mean, let us not consider this diffraction things, right? Angular resolution theta is given by this famous 1.22 lambda by t. So what I want you to tell is alpha is a small for obvious reasons because the distance is really big. And from simple trigonometry, suppose this distance is d, I've already given here. Um, tan alpha will be 2r by d, and we have already talked in our previous video. It's 2r, small angle approximation. So from this, what we're also given is alpha is at least greater than or equals to theta. Like it must, right? So 2r by d will be greater or equals to 1.22 lambda by d. This thing is just this angle um minimum angle that a telescope can distinguish between two objects. What I mean is, suppose um there are two stars, right? For a telescope which has a really small aperture from a certain distance d, let's suppose, it will see these two different objects as a single object. But for a telescope which has a reasonable aperture, which means it has a reasonable this theta thing right here, we would have easily distinguish these two objects. That is simply what it means by this minimum angle needed for a telescope to reach, which is 1.22 lambda by d. So this is just it. Therefore, distance is yes. We have escape velocity as this right here. And we know for a black hole, escape velocity will be greater than speed of light. Okay, now what we have is R, an effect of the photon capsule radius. So it will be 3 times R. So in terms of R, we will have this R divided by 3, or it will just be easy as this, I suppose. 6, 6 cm divided by c square. Just as easy as this. So now the opposite diameter needed will be at least greater than or equals to 2 times 6 cm by c squared, which is 2 lambda d c square by 12 d m. That is the required question. Mhm. So now for question number B, it is just about plugging in the values into this lovely relation that we will get for question number 1. Answer would be around 1.1 times the radius of Earth. I suppose it is 7,400 kilometer, I guess. And for the question number 2, it is around 1 or right. So it would be equal to 6,000. It's easy one. So for question number 3 that you were talking about, what type of technology is needed? Um, for obvious reasons, an array of radio telescopes, right? Interferometry. Because as we see here, just to resolve those, we have this crazy aperture radius as 7,200 kilometer and 6,400 kilometer, roughly just size of Earth, radius of Earth. And these are actually crazy ones. And actually, the Event Horizon Telescope is based on this interferometry, while we install this array of radio telescope working at a wavelength of 1.3 mm. And yeah, it is just it. So, yep, from and these telescopes are spread into various locations, so not so answer will be B. So I will suppose this question is really good. I mean, how much radius the Earth's orbit really increases as a result of Sun losing mass due to thermonucleic reactions in its century. So we do need this relation, Einstein's mass energy equivalence. Let's take luminosity as L naught, then we have dm naught by dt, right? Yes, rate of loss of mass. So we have this equals mc squared. Now L naught will be equals to, since this is this, this rate of sense of mass, let us consider it right here. L naught will be that, then multiplied by c square, then dm naught divided by dt. Okay, sorry, will be equal to minus L naught c square. So there are a couple of ways, but certain theories that we need for this is like isotropic radiation, which is, I mean, h times v out is constant, right? All of things. So what we know is sun loses mass at a rate dm by dt is equals to L naught by c squared, right? So by this, what we can tell, we have L naught as 3.83 times 10 to the power 26, right? So we will have dm divided by dt as, mm, you know, let's just consider as this, which is equal to 3.83 times 10 to the power 26 divided by 3 times 10 to the power 8 squared, which comes approximately as 4.26 times 10 to the power 9 kg per second, right? So what is the mass lost in 100 years? Convert 100 years into seconds. It comes roughly as 3.156 times 10 to the power 9 seconds. Just multiply 100 with 365.25, then 24, then 3600, all this stuff. So to calculate the delta M, which is this mass lost in 100 years, we'll have L divided by C square multiplied by T. You know, mass lost in 1 year, then for 100 years, this multiplied by T. So that will be equal as this thing right here, right? Multiplied by this thing right. As mean, um, just multiply this with this. So what we'll get as an answer is 4.26 times 10 to the power 9 multiplied by 2.156 times 10 to the power 9. So that will come as, I guess, 1.34 times 10 to the power 19 AZ per second, and multiply by second. That will be right there. So now, to calculate the fractional mass loss, we have the solar mass as 1.99. Well, let's consider it 2 times 10 to the power 30 kg. So delta M divided by M naught would approximately come as we have delta M as this and mass of the sun as this. Then just, you know, divide them. We will have 6.74. Okay, sorry. 6.74 multiplied by 10 to the power minus 2, right? So for this, we'll need to proceed further, we'll need to learn about this relation between orbit radius and solar mass. So we have um relation between orbit radius and solar mass, right? We'll have L equals, am I recording? Yes. L equals M with CMA. We know M and A, it's a constant, right? There's a constant. So we'll have MA equals constant. So by this easy thing right here, like we have learned this in asterisk class as well. Just this, you know, in error calculation as well. We need this thing, multiply it right there. A equals 1 AU, which is the Earth's orbital radius, right? Let us consider this all this thing orbit as a circular, then we'll consider A is 1 AU, the average distance between Earth and the Sun. So the fractional sense, that we'll get is 1.496 times 10 to the power 11 multiplied by 6.74 times 10 to the power minus 12, which is this. And as an answer, we will get 1.01 or 03, I guess. Yeah. So it is this much meter. Therefore, delta A equals 1 meter is the answer, which is the change. Uh, it's the change in Earth's radius of the Earth's orbit. That's it. That's it. Well, interesting question. Actually, it's mass energy equivalence, isotropic radiation. It is so h times we consider as constant. Then we get GMMM. I mean, the gravitational constant is equal to this centripetal force. Then we will get this, you know, formula as Gm by R minus R, which is Cm. So, and M times R will be constant. So, these all things. This question can be done in a lot complicated ways than I've done it, but I suppose this is the answer for it. Just prank to you. Okay, now we have this third question. The hydrostatic equilibrium within the sun can be expressed with the following expression: dp by dr equals minus cmr by r square density. So let me tell you this, that dp by dr. How? So stability condition is pressure force equals gravity force. Everybody knows this. Pressure change with radius minus cmr density by r square. Why is it negative? It's negative because dv by dr is how fast pressure changes with radius, and when you move outward, we have pressure will decrease, right, as you move outward. So it's negative. So we have dp by dr equals minus cmr density by r squared. Now, what we have is this, just pull in the formula right here, by 3 pi r cube divided by density r is therefore will be equal to, I hope you understand. Now we have this pressure gradient proportional to radius. Now, as we want the pressure only, what we need to do is integrate this, right? So we will have dp equals minus 4 by 3 pi z density squared dr. Now we just need to integrate from the surface to the center, right? Because at the surface, I'm sorry, the R will be equal to 0, pressure will be equal to this, and at the center, pressure is PE. Center pressure is what? Let us denote it by PC, personal computer. Fine. So it's going to be 0 to PC, PP value is equation minus 4 by 3 by, we have this right here. Yep, just integration, just right here. R, R, there to R. Now, now what we do have is this right here, minus 4 by 3 by the density square, and as it is only depending upon r, we have r squared divided by 2 minus 4 by 3 by z square. Easy one, right? Easy one. So the spacey thing right here, spacey minus same thing, equals to 2 by 3 pi. What do we have? This density squared square, right? I got this. So this is this pressure at the very center. It's the pressure at the very center. So what we also do have is density is 3m divided by 4 pi r cube, right? So it is just this general formula. You might want to just write it down. It's actually really easy. Square it just right there, or we- and then we will have this pressure at the center as 2 by 3 pi zr cube multiplied by this thing right here, and then we will have EC, which is pressure, VGM squared divided by 8 pi r. Powerful. We will use this, but anyways. So what is the numerical value for sun? The numerical value of sun, m naught, take it as 10 to the power 30 kg, right? And then radius is 109 times. We will just do this, but anyways, we know the exact one. I think it is this one. So this will give BC equals 3z m squared divided by 8 by r4. Let me take my calculator. 3 times 6.67 times 10 to the power minus 11 multiplied by this breaking mass right here, divided by 8 times pi times 6.96 times. We have 1.34 times 10 to the power 14 pascals, and that's the answer. So actual sun's pressure is about 2.5 times 10 to the power 16, I guess. So this, and this is 200 times more. But these things, like, it is, the core is much denser than the outer layers. Sun is not of a uniform density. We considered it as a uniform density right here. So, and this is the answer. Beautiful question, really beautiful. I I think, yeah. Let us do some 2 to 3 easy questions and wrap it up for today. One of the reasons I love IOA, it has really fun questions. We are in the question number 4. Estimate the radius of a planet that man can escape its gravitation by, particularly assume density of planet SM. So let us suppose that one man can jump up to 50 centimeters. You can do it practically, right? So it can be, it's a rough estimate, right? So you can choose between like 20, 30 centimeter, 50 centimeter. If you're Ronaldo, it's 70 centimeter maybe, I don't know. So so we will have jump, we'll have when to calculate this escape velocity and the jump. So for the jump, it's going to be, and for escape, rotation divided. So let us equate. So 2cm, I'm sorry, 2zh will equal 2cm by r. Then it will be equal to, with, just change it to this density thing right here, right? And then just calculate the radius, right? So it will be 3zh divided by 4 pi density. This is one of the easiest and the fun questions. So just, you know Add this value yourself. Z as 9.8, S as anything like 0.5 meter, I guess. Yep. And for pi, and density is just density, I'll tell you it is 5,515, rock density of the crust, right? 5,515 kg per meter cube, and gravity is a small constant, which would roughly come equal to this much, which is around 1.8 kilometer. Yeah. So radius of that planet would have to be 1.8 kilometer, then by just jumping will escape that planet. So crazy. Now, another question that we do have: a spacecraft landed on the surface of a spherical asteroid with negligible rotation, whose diameter is 2.2 kilometer, um, and its average density is 2.2 grams. Cube. Can the astronaut complete a circle along the equator of the asteroid on the foot within 2.2 hours? Right. So we're talking about orbiting of the astronaut. We're talking about we need to just find the velocity right here. It's going to be an easy concept right here. So now for question number 5, what we need to calculate, let us suppose m is 4 by 3 pi r cube density 4 by 3 pi. Then what are we given right here is um diameter is 2.2 kilometer, then radius 1.1 times 10 is about 3 cube multiplied by density. We do have 2.2 times 10. Then we will have um this much, as I have calculated, 1.23 times 10 to the power 13 kg. Remember that 2.2 gram per centimeter cube would equal to this value right here, because this is this equivalent value, like 2.2 gram per centimeter cube equals to 1000 divided by 100 divided by 100. Oh, I'm sorry, 1000 divided by 100, 100, 10 to the power minus 3. So times 1 times power 3 cube times 2 power this much. And it would be just crazy if you know that. I suppose I've done it in 2.2 kilometers, 2.2 hours, and 20 gram per centimeter cube. You will take this, you just have this rough estimation, right? Then we consider mass of an asteroid is very, very smaller than this big thing right here, of course. So mass of an astronaut is very, very small than this. So then it can be ignored. Then the critical velocity will be equal to root gm by r. Just plug in the formulas. It is 1.23 times 10 to the power 13 multiplied by 1100, which is the radius in meters. So it will come as 0. Um, yes, it will come as 0.86 kilometers per second. Right? Actually, really easy question. It's kilogram here. So now what we are asked is, can the astronaut complete a circle along the equator? Right. So if the velocity of the astronaut is greater than the critical velocity, then he will start orbiting the satellite. Then by this, it will mean that he will not be able to walk on satellite, right? So if the astronaut wants to complete a circle along the equator, I mean equator of the asteroid on foot with 2.2 hours, not orbit but walk, then we will have this v2 as 2 pi times 1100 multiplied by 2 times 3600. And this will come approximately as equal to this, which is 0.86 kilometers per second, right? So as v2 is greater than the critical velocity, then you know he will not be able to complete the circle with this given time. It can be much bigger. You know, it came approximately equal, right? But it is at least greater than this one, this velocity, critical velocity right here. So, yep, it is this. So now let's get on to the next question. I suppose estimate the mass of a globular cluster with the radius of 20 parsec and root mean square velocity of a star in this cluster is 3. I don't suppose this is the question of data analysis. This is one of the easiest questions, I guess. So, um, we are given that we know that escape velocity is just root 2 multiplied by v is RMS speed. So we have this convenient assumption where one we can make one can make any assumption. So we have this kinetic energy, which is obviously equal to divided by r, right? So escape velocity, of course, right? Therefore, P RMS squared from the above relation Dm divided by L. Now, now, what we need to do, what we need to do is, square and 2 will cancel out. This is an easy one. So what we need to do is calculate the mass. So r multiplied by v RMS squared divided by the gravitational constant. We have r as 20 pc and 3 kilometers. Fine. So 20 pc, then will cos then 9 times 10 to the power 6 divided by 6.72 times 10 to the power. Yeah, this I like to use 6.67 times 10 to the power minus 11, but yep, 6.672. So 20 parsecs, 20 multiplied by the parsecs times, and this is the square value, like it is the value which you will get, and it is approximately equal to how much it was. Mm, I suppose the answer will come like this. Yes, so 8.32 10 to the power. What? That's so the mass will be, you know, this much of the mass of it. Easy one, easy one. This mass of the global cluster is very much by a lot factor than the sun, because mass of the sun 2 times 10 to the power 30 kg. So just divide it with that and you get the relation. And in exams like this, it is typically really good to compute it like this, right? So 5.3 times 10 to the power divided by 4.2 times power. Mm, suppose so this is it for today. Um, I suppose my brain worked well and I solved a lot of problems. I suppose there are no numerical errors in these questions. These are actually easy questions. Make sure you know the video. Let's go.